Welcome to the last episode of the first chapter of our Reintroduction to Programming with Odes. We started off this journey with the goal of writing some executables from scratch. We talked about binary, about file formats, about assembly, about memory in the C video, and about data and program structure in the stack video. Now, having learned all this, writing executables is going to be almost too easy. I mean almost. There'll still be a lot of numbers to wade through, but once we've waded through them, we're going to have a relatively simple way to write relatively simple programs out of pure bytes. Today we're going to build Linux x86-64 ELF or ELF executable programs. If you're on Apple Silicon, there's a path for you too, which I'll come to later in the video. You might be wondering what ELF stands for, and I will tell you that right after I say these words. ELF stands for Executable and Linkable Format. That means it's a format for storing executable machine code. Sometimes it stores executable programs that you might run, sometimes it stores shared libraries, and sometimes it stores object code, the in-between products that compilers produce before they get turned into full executable programs. Today we're focused on executable programs. The ELF format is the standard for Linux, so we'll also be focusing on Linux today, and in particular on x86-64 Linux. I've chosen ELF because it's probably the simplest format to get started with. Let's talk about the job of an ELF executable. Let's imagine we want to run a program called hello, and to do this we'll need an area of memory. Before we can start the program, somewhere in that area we're going to need to put some machine code, and somewhere else we might put data that our program needs to work, like strings to print out or areas of memory that we might read user input into. The operating system will also want to take up parts of that memory space to set up a stack amongst a number of other things. We'll then need to point the processor at an address in memory and tell it to start executing code. To achieve this outcome, an ELF executable contains two key things. The first is the actual data that it needs to put into memory, and the second is metadata, which tells a part of the operating system called the loader how to construct the proper memory image out of this ELF file and get it running. It will do this by specifying that the loader should go to such and such an offset in the file, read so many bytes from that position, and place it into a particular address in memory with specific permissions. The ELF file also specifies the entry point address, the place at which the operating system should point the processor and tell it to start executing. I'm talking about the simplest possible executables here. When you start to look into the real programs on your computer, let's say if you open them in a hex editor, there's quite a bit more built on top to do with other things like dynamic linking, address randomization, and similar things like that, but the core ideas still apply. Let's take a look through the parts of a small but functional ELF executable. First, we have the ELF header, which I've split into two parts. The first being the ELF identity header, which tells us that this is an ELF file and some other basic information about its format. This takes up the first 16 bytes. Secondly, we have the ELF header proper, so the rest of the ELF header, which tells us a few other things, whether it's an executable or a library or whatever, the instruction set architecture, the entry point address, the offset and sizes for certain important bits of metadata, and a few other bits besides that. And after that, we have the program header table. In this table goes the entries which tell our loader which bits of the file to load into memory and where to put them. We often refer to the parts of file or memory that the program headers refer to as segments. Program headers also sometimes do other things, but largely they're for loading data into memory. In the ELF format, there is an important distinction between two quite similar words: segments and sections. I've just spoken to you about segments. They are parts of the file or memory specified by the program headers. Sections are different. I'm going to tell you only three things about sections today. Firstly, sections define areas of the file, just like segments do. Secondly, sections are typically used by compilers and linkers to manipulate objects and executables. When I say objects there, I mean object files, not sort of classes and object-oriented programming objects. And thirdly, if a program does not depend on shared libraries, then it does not absolutely require sections to run. We'll probably talk about sections in a future video, but not right now, and this program does not have any. The rest of the file is just space where we can put stuff that we want to load into memory. A normal executable might have loads of blank zero-filled space in it for reasons we'll get into later, but I wanted to fit this one on the screen, so I've kept it pretty packed together. I'll highlight two areas that I've put data in this file. The first is where I've put the x86-64 machine code, which is going to print out a message and then exit. The second is where I've put the string that we want to print. In this executable, we have two program headers which are going to load these bits of data into memory at two separate locations with different permissions. This is sort of pointless in a program this small, but I thought having two segments might illustrate the way the format works better. The usual quirk of binary file formats means that you can't really start at the beginning and write the headers first, because you need to know how big your data is going to be before you can write a header for it. So next we're going to talk about how we convert assembly code into machine code. Once we have the machine code, we can construct our ELF file. Let's take a single instruction, in this case to move the immediate value 1 into the register EBX. Recall that the E means it's the lower 32 bits of the 64-bit register RBX. And the E stands for extended, in case you're interested. I don't know what the R stands for. Probably really extended. Please don't remember that. I'm almost certain it does not stand for really extended. Anyway, this instruction corresponds to the hex C7 C3 01 000000. This breaks down into C7, which is the opcode, C3, the mod R/M byte, which we'll talk more about in a moment, and 4 bytes representing the value itself. An opcode is a hex code. I guess it's actually it could be any number, but conventionally it's a hex code representing a specific operation. What you know of as a MOV is actually a collection of at least 13 opcodes plus a number of modifiers, which takes it up to, I think, at least 32 different variants of this instruction. The C7 opcode specifically refers to moving an immediate value into either a register or a memory location specified by a register. There are opcodes which will only move immediate values into registers, as well as opcodes which will move from registers to registers, and we'll do all of this in various different sizes and different modes. So you might have thought that the assembly we were using before was just translating assembly instructions pretty much straight down into opcodes directly, but it actually does have to have quite some degree of intelligence to work out which one to use. Since we're writing machine code directly though, we have to use our own intelligence. So on the off chance that somebody is watching this who actually already knows all of the x86-64 opcodes off by heart, and I'm going to guarantee, based on the audience that I have, that someone at some point is going to come along and watch this who does know this. If you're wondering why I didn't use the B8 opcode, where you encode the register into the last 3 bits of the opcode instead of into the separate mod R/M byte, that would definitely have been a better opcode for this task. But I, 1, didn't see it, and 2, if I had done that, I wouldn't have the opportunity to tell you about the mod RM byte, which I think is pretty cool. The mod RM byte allows us to specify, in this case, where we want our immediate value to go, but in other cases it could specify a whole host of other things about destinations and possibly sometimes even sources. In this case, since we're putting the value straight into a register, we encode 1 into the first chunk of 2 bits, 0 into the next 3, which is called the opcode extension in this case, meaning that it further breaks down the behavior of the opcode, and then use the last 3 bits to specify our destination register. If we were doing something else like moving the value of a register into a memory location specified inside a register, we could also use the mod RM byte to do that. But in this case, we're just moving an immediate value straight in. Then we have the immediate literal value that we want to move into the register. In this case, 1 encoded as a 32-bit little endian value. And if the term little endian is blowing your mind at this point, I suggest you go back and watch the bitmap video where I talk about all of that. Here's our little program getting converted into hex and binary by a mysterious blue squectangle. First, it prints out a message using the write syscall, and then it exits. The address here, 6000F0, is the address of our string in memory after it's all been arranged by the loader. Now if you're thinking, okay, so we need to know the location of the data to write the instructions, and then we need to know the location and size and all that of the instructions in order to write the headers, and you're starting to think, well, this is getting a bit messy. Well, if you ever wondered why a linker is so important, then that's one reason why. Addresses can get really confusing when you're writing unaided machine code. I will say there's nothing that makes you appreciate assembly like writing machine code directly. It's kind of fun, but I wouldn't want to do it all the time. Let's lay out our file piece by piece. We start with the identity header and the magic number, which identifies this as an ELF file. Then we specify the class of the file, whether it's 64 or 32 bits. Then it's endianness, and we've got little endian here. The version number comes next, which is always 1. If you ever release a version 2, you'll know something big has happened. Then we specify the binary interface our program will have to conform to. I think for this program we can leave it 0 and it works fine, but if you're doing dynamic linking, then I think you need to be more specific than that. We specify the ABI a little further with this extra version byte, and then we have some reserved space, which I guess they might use in ELF version 2. Moving on to the ELF header proper, we specify the type of the file, which is for us an executable. Then we specify the machine architecture we're targeting, which is in this case x86-64. We specify the version again for some reason, and then we start getting to the good stuff. Here we specify the entry point, the address that the operating system should point the processor at to start running the program. So adding those together, we get 4000C0, which we encode in little endian and put in the file. Next, we need to specify the offset in this file that the loader is going to find the program header table. We'll put this just after the ELF header at offset 40. We now have a field to specify the offset of the section header table, but since we don't have any sections, we leave it 0. We have some flags which we leave blank. Then we specify for some reason the size of the header we're writing right now. And I think for 64-bit executables at least, it's always going to be 40. Next, we specify the size of each entry in the program headers table. So that's one entry, not all the entries together. This will, for 64-bit executables, be 38. And after that, the number of entries that are going to go in the program headers table, and we'll have 2 of them. We then have the same info for the sections table as well as the index of the section which specifies the section names, and we ignore all of these. Now we move on to writing our program header table. Our first program header is going to be the segment in which our machine code is going to execute. This first 32-bit value specifies the type of the program header, and in this case we're going to choose PT load, which will tell the loader to load this segment into memory. Next, we specify the permissions for the memory segment, which are the ways in which this area of memory is allowed to be accessed. Just like Unix file permissions, we have executable, writable, and readable. We want our segment to be readable and executable, so we OR those values and get 5. Next, we specify the offset in the file that our segment starts. In this very tiny example, we're constrained by a few factors to make this 0, meaning we'll load from the start of our file. The first factor is that the loader on any particular system wants to load in segments which are aligned to what's called page boundaries. A page is a chunk of memory, and a particular system allocates memory in page-sized chunks. Since the page size on our system is 4096 or hex 1000 bytes, it means they should start at addresses which are a multiple of 4096 or a multiple of 1000 hex, which is easier to see. We could shift our code out to address hex 1000, and that might in some ways be quite nice, but it would make this diagram a little big, so I'm going to keep it all condensed close together. There's one more reason we're starting here, which is that my system wants the first segment to load from address 0 so that all the headers get loaded into memory, which I guess makes sense. I've noticed that not all systems seem to require this in the format, but mine does, so I've kept it that way. In any case, we're loading from offset 0. We then need to specify the address the loader should load this data into. We pick 400000, which is a conventional place for executable code to go. There's then an area to specify the physical location if it's relevant, which for us it isn't, so we skip it. Next, we specify the size in the file of the data we want to load. We specify E8, which will stop right at the end of the instructions. I don't actually know if the loader will respect this. It might just load the full page worth of data, but it makes a nice example, so E8 it is. Then we specify the size of the segment in memory. This might be larger than the size of our data if we wanted to have a large segment filled with zeros. For us, we'll keep it at the size of our data. And again, I don't know exactly how the loader will behave when this is smaller than the page size. I'm kind of hoping that it will cut it off because otherwise the permissions story won't be as good, but I couldn't find any clear data on that. Finally, we specify the alignment, which for us is hex 1000. This might seem redundant, but I believe it lets us specify that our segment is going to have at least up to a full alignment multiples worth of space after it finishes, assuming that it doesn't finish exactly on a boundary. Now we'll move on to our second program header. This is going to load in a read-only data segment which we'll use for our string to print out. We're going to load in the whole program again for alignment reasons, but with a few differences. The first is that we'll give it read permissions rather than read and execute. The second is we'll load it into address 600000 rather than address 400000, and we'll load in a full memory page worth to capture our string too. And I'm doing this mostly to illustrate that this is how ELF files work. We could have technically done all this with a single segment. We then have some padding to get us up to address C0 where we said our instructions would start, and also to illustrate the point that these files are typically not packed very tightly. Then we load in our machine code. Because it's x86-64 and each instruction might be a different length, it doesn't always line up nicely, which glitches out my visualization a little bit. Once we're done with all these instructions, we add a little bit more padding to get to the offset for our string data. Then we put it all in and add some zeros to make it line up real nice. Really completely unnecessary, but it made me happy to see it all line up. And there we have it, a working executable in 256 bytes. Let's take a look at it loaded into memory. Now we need to talk about virtual memory. Each process is given a very big area of virtual memory. I think it's on the order of thousands of petabytes of space all for its own. It's private, just for that process and the operating system's interactions with that process. Very little of this memory actually exists. That's why it's called virtual memory. To create this illusion, the operating system works together with a part of the processor called a memory management unit. They work behind the scenes to map parts of this virtual address space to physical memory in the RAM, or even data which is not in RAM but could be loaded if requested. The operating system manages this memory space in chunks called pages, like we discussed before, typically loading or unloading a page's worth of memory at a time. This is useful because it lets each process have its own arbitrarily large and private memory space to do with what it wishes without having to actually allocate all of the computer's memory over to a single process, or having to parcel out limited chunks of memory to each process, which each might not use very much of at one time. It also helps us get around processes being able to simply reach into the memory of other processes like they could in the olden days of 16-bit unprotected mode. See, just when you think you're getting close to the machine, another layer of abstraction shows up. If we want to get underneath this one, we'll need to build our own operating system or work without one, but I think that's one for a future video rather than right now. In this virtual memory space, we find our code and data segments, plus a few other things the operating system sets up for us, like stack and heap space. The operating system stuff will typically go in the higher half of the memory, so we mostly stick to the lower half for our stuff. Like I said before, we've essentially loaded the whole executable into memory twice for the purposes of our example. But if our executable was bigger, then we might have loaded the first 4096 bytes into one segment, the second 4096 byte into another segment elsewhere, and so on. Because this space is so large, both of our segments are operating a really tiny area right at the low addresses. Even this diagram understates how small an area this is. In reality, both segments would be within a fraction of the first pixel of this memory bar. Consider how even the first hex digit in this address will split this bar into 16 stripes, and the next hex digit will split each one of those 16 stripes into a further 16 stripes, and the next into a further 16, and so on. It's very big. It's not atoms in the universe level, but it's a big space. You can also see that the address of our entry point, 4000C0, ends up being the address of our first instruction, as it should. Within the instruction which specifies the address of our string, we can see the address 6000F0, which is the address our string ends up at. In a real program, we'd have to jump through a few hoops to resolve this address from a symbol or an offset. But since we're writing by hand, we can specify it directly. Having gotten the virtual memory set up, the operating system points the processor at the address of our first instruction and sets it going. And that's it. From instructions to executable to running process. I actually challenged myself to hand type the hex of this executable to a file and run it to show you it works. I know obviously I'm still working through a million layers of abstraction, but it's fun to imagine just typing out an executable program by hand and it really running. It took me 4 attempts to get right, and you can try to guess which one is the one where it works if you like. There was a particularly fun one where I got it mostly right, but I forgot that exclamation marks were special in Bash, and so it didn't work at all. So there we go. I'm the human assembler. You can try this out yourself if you like. If you can memorize all the bytes and type them out on command, that could be a pretty fun party trick if you hang around with people who would find that impressive. Once you've done that though, it's not a lot of fun to do it again, so let's build a very small framework for constructing these ELF files, and then we can play around with it and build some stuff. And here it is. I'll talk you through it, and there's a link on the ODES website so you can play with it yourself as well. Firstly, I use an Apple Silicon Mac, so I'm going to use the built-in dev container to set up a virtual x86-64 environment using Docker and Rosetta 2. It's pretty neat. You just select reopen in container, and VS Code figures it all out to open your current directory in that environment, along with the terminal and everything else. Let's see the project run. This example here creates an ELF executable that prints hello world. When I run the script, it outputs a binary to the build directory. Then I need to use chmod, or as I pronounce it in my head, chmod, to mark it as executable, and when we run it we get hello world. The code works by setting up a collection of placements. A placement is an offset in the file and some data to put there. This is file offsets, remember, not virtual memory offsets. Then when we call writeELF with a list of placements, it will create a file with the right data in the right places. We've got a placement for data at the top, which is our message. Note that we're using the B prefix on the string to indicate that it's a byte string and shouldn't be interpreted as UTF-8 or anything like that. We place that in the file at offset F0. Then we've got our code placement. We give it the offset C0 and then a list of bytes. We construct that list of bytes by calling functions which themselves return lists of bytes. The asterisk spread operator makes sure all the values get flattened out so that we don't have a list of lists, but instead a list of all the values in those lists. We'll look some more at those functions in a moment, but they're very simple. Then we call writeELF with a file name and a list of placements. At the end, you can see our code and data placements, but we've also got our headers in there too. We've got a series of helper functions which take the arguments we might want to fiddle with and return the right bytes corresponding. Now, if we look inside elf.py, we can see that writeElf function, which just opens a file in write binary mode, then goes through each placement, seeks to the right offset in the file, and writes it out using the byte array functions to convert it into bytes. Below this, we have our placements data class. It has all the attributes you'd expect, as well as helper methods for the size of the placement and also how far it extends into the file. Extent is useful if, say, we want to know how much of the file we need to tell the loader to load to ensure it captures everything up until the end of this placement. You can see below the helper function for constructing the elf identifier header. Again, just the right lists of bytes that make up the file format we saw earlier. Now I think of it, I probably should have put these lowercase. I just always see them in the docs as uppercase, so I wanted them uppercase. Anyway, it still works just fine. The other helpers are much the same. These helper functions le16 and le32 and such are to encode a numeric value as little endian bytes, and we'll look at those later. Now let's look at the instructions helpers. They're very similar. They take arguments and return lists of the right bytes to match what you want them to do. The function mov_r32_im32 moves an immediate 32-bit value into a 32-bit register. It does this by first getting the right bit string for the register we pass it, then returning the opcode along with the mod r/m byte with the register ordered into it, and then the immediate value little endian encoded. And syscall is even simpler, it's just a list of 2 bytes. The regcode function converts register names into their equivalent number so that we can put them in the mod r/m byte. It does this by taking the last 2 characters, so AX for EAX or RAX, and then looking them up in this dictionary. You treat the single byte registers a bit specially, so there's some provision for that, though we're not actually using it here. Also, if you want to use the higher registers like R9, you'll need to do a little bit more work yourself. Now let's look at the endian converters. They're again nothing special if you've been following this series. They use and bit shifting to grab the last byte out of the number a particular number of times. All pretty straightforward. We've got a function that writes lists of bytes to a file at specific locations, and to make it nicer to work with, we create helper functions which return lists of bytes in the right format to do what we intend, and these themselves can use their own helper functions. I thought it might be fun to build a quine with this framework. Quine is a program which outputs its own source code without taking any input other than running. But typically it's human readable source code rather than machine code, so I'm pretty sure this isn't actually a real quine, but it's a good way to illustrate the ELF format. You can see here that if we pipe the output of the ELF quine to a new file, we get the exact same file as our original quine. We can even run it and get a third iteration. You can see how this works on the left. We have a program header to load in our code to run at segment, I think it's 400,000 like normal, but we also have a program header which instructs the loader to load the whole executable to address 200,000. Having done that, we can then write our assembly so that it calls the write syscall to standard out, but with this address pointed at address 200,000. Given that, it will then write out our executable, and after that we exit. Another thing I'll point out about this code is that I've used Python functions to create reusable assembly macros. I could potentially reuse sub show for something else. You can use this macro approach to build up even more sophisticated higher level language abstractions too, which is actually the topic of this video's members only exercise. And speaking of exercises, this video, like every other ODES video, has a page on the ODES website with resources and exercises. For resources, I've collected some pages you might find useful on writing the ELF format, as well as x86 instructions, plus some instructions on how to use Rosetta 2 and Docker to set up a x86 64 image on a Mac. In the exercises, we've got an optional exercise on writing your own framework like the one I made in this video, or you can use the one that I provided, but you might find it fun to write the framework in your language of choice. Then you'll build a version of the quine that I've just shown you, but self-modifying. So the quine will output a new version of the quine each time, which does something slightly different. Plus, there's an exercise for ODES members, to whom I'm very grateful for supporting this project and for me to make these videos. This one I think is particularly interesting because it builds on some of the stuff we've seen so far to create some higher level language concepts purely through assembly macros. So if you're interested in that and you want to join as a member, then there's a link in the description to the ODES website and all kinds of buttons which will lead you to the right place. This video concludes the first chapter of the Reintroduction to Programming series within the ODES project. In it, we've gone from binary all the way to writing executable programs from scratch, so I'm pretty pleased with how that's gone. The next 2 videos are going to be a little interlude before we start a Reintroduction to Programming series 2. The next one will be an errata and Q&A video. So if you're a textbook writer and you find that there's an error in your work or clarification that could be necessary, you can't just recall all of your books. So what textbook writers do is they link to a page, typically on the internet or in some periodical, where they write up periodically the things that they've identified that could be clarified about what they've done or corrected. And YouTube's kind of similar in that you can't actually edit old videos. You can change the description and comments and stuff, but you can't actually go in and edit them like you would a web page or something like that. So at the end of each chapter, I'm going to do an errata video where I go through all of the comments, all of my own notes, and dig into some areas where I need to correct something, or areas where I think a bit more focus on a particular area would have added some clarity. Also, where somebody's added a particularly valuable comment that I think deserves highlighting, I will add that as well. But it's not just going to be a straight list of stuff. It'll still be fairly interesting and engaging, and we'll dig into some of the topics behind the different things that we're covering there. So it should be, I think, pretty interesting. Plus, I'll also be doing a Q&A. So if you've got any questions you want to ask, then you can leave them in a comment, in which case I will treat them as public, or you can send me an email, in which case, unless you tell me, I will treat them as private. The deadline for questions will be September 30th, and the deal with the questions is, as long as you're okay with me not necessarily answering it, either for time reasons or because it's a duplicate or something similar to that, and as long as the question is not obviously nasty, then you can ask whatever you like. So September 30th, and a bunch of you have already asked some questions, so I'll probably go through those as well. I'll also be working on some updates to the website, a project for members, and of course planning chapter 2, as well as a few other projects which I will announce when they become relevant. Finally, and off script now for the moment, certainly off script anyway, I have an idea. You'll be able to tell I'm off script because I'm already rambling. Thank you so much for being part of this project in whatever way, whether it's watching this, and you must be watching this because otherwise you wouldn't be hearing this. Yes, thank you, members, especially for supporting me to work on the project, but actually everyone who's watched, commented, liked, whatever it is. It's been really fun for me and actually a really enriching project. So thank you so much, and I look forward to speaking to you again for the Q&A and errata, and then another video which I haven't quite planned out what it'll be yet, and then in chapter 2. See you soon.